Hello there, everybody. We're now going to start section 4.2. So to review, an event is any collection of results or outcomes of a procedure. Usually you only have one thing you're looking at. A simple event is only one outcome that cannot be broken down any further. And the sample space consists of all of the possible simple events. The sample space has to include every possible outcome. Okay, so let's talk about a really important idea called disjoint events. Disjoint events are two events that both cannot happen at the same time. So disjoint means either one or the other or neither of them will happen, but they cannot both happen. So here's some examples. Imagine you flip a coin. Heads and tails are disjoint events because you cannot flip a coin and get heads and tails. Like, that's a really bizarre coin in another dimension or something. Just kidding. So heads and tails are disjoint because you cannot flip heads and tails at the same time. And again, notice the key words "at the same time." It's perfectly possible to flip it multiple times and get different outcomes each time. But what I'm saying is you only flip it once. You cannot get heads and tails at the same time, so therefore they are disjoint events. Here's another example. If you roll a die, that's just a regular dice, all 6 outcomes are disjoint, because you can't get a 2 and a 3 at the same time. Now here's how this relates to us a little bit, because we're going to be doing statistics. In a survey, picking 2 different people in the population would be disjoint events. Think about that. If I give a survey to one person and I give a survey to another person, they're 2 different people. Those are 2 disjoint outcomes. They're both going to give me results that are independent of each other. So this is going to start to brush into some statistics here in a second. The problem with disjoint... never mind, let's keep going. So as a reminder, we learned in the previous videos that the complement of an event, the probability of the complement, so the complement is something not happening, and so the probability of the complement is 1 minus the probability of the event happening. So the probability of a complement is equal to 1 minus the probability of the event happening. And remember that they add up to 1. And so, for example, if it's 30% chance of rain, that's A. 70% chance of no rain, that means that would add up to 100%. Those are all the possible outcomes. So here is an example. If the probability of getting in a car wreck on the way to Denver is 0.3%, what's the probability of not getting in a car wreck? So the probability of getting in a car wreck on the way to Denver is 0.3%. What's the probability of not getting in a car wreck? Remember, first we should always convert percentages to decimals before we do any math with them. So I'm going to convert the probability of getting in a wreck to 0.003 because that's 0.3%. You move the decimal 2 places and that gives us 0.003. So that means that the probability of no wreck is equal to 1 minus that probability. And so that's 1 minus 0.003. So there's a 99.7% chance that we do not get in a wreck on the way to Denver. So that's good news. We don't want to be getting in any wrecks. So 99.7% chance of no wreck. That's the complement of 0.3%. And notice that if we added these together, we'd get 100%. As I mentioned, it's always a good idea to convert your percentages to decimals before you try to do math. Here's another example. The probability of not being satisfied by the final episode of your favorite show is 23%. And I'm sure all of you have an example of this, I'm sure. So the probability of not being satisfied by the final episode is 23%. In that case, what's the probability of being satisfied? Well, we can do the complement. So first convert that to a decimal, 0.23. And then do 1 minus that to get the probability of being satisfied. So you can see here that the probability of being satisfied is 77%. That's a good thing. Okay, so now we're going to talk about a really important idea that's a little confusing. This is called the addition rule of probability. I want you to imagine the following. Let's say you need to go shopping for something, and that the probability that the store does not have the item you want is 40%. So the probability that you go to the store and it doesn't have the thing you want is 40%. Now, imagine that Another thing that can happen is you get stuck at a red light. And let's pretend that there's an 85% chance you get stuck at the red light. Maybe there's a lot of traffic and the red light is terrible and you have terrible timing, and so you have an 85% chance of getting the red light. The question I have for you is, what is the probability that both of these happen? That's like a really bad day, right? What's the probability that both of these happen? You get stuck at the red light and it doesn't have the item you want anyway. Well, we know that because these are independent events, because they don't affect each other, the way to calculate the probability of both of them is to multiply. And so you multiply 0.40 times 0.85, and so you see that we have a 34% chance, that the store doesn't have what we want and we get stuck at the red light. So that's answering the and question. What's the probability of it not having what we want and red light? Now I want to ask you this question. What's the probability of getting the red light or the store not having the item you want? Do you see how that's a slightly different question? What's the probability of getting stuck at a red light or the store not having what you want? Either one or the other. Now, the problem here is we can't just add these probabilities together. Because if we add 40 plus 85, we're going to get a number that's over 100. So that's not very helpful. So how do we calculate this? Something else must be happening. Something else must be going on, because we can't just add 40 to 85 because we get 125, and that's not a probability because it's greater than 100. So let me show you how we do this. This is called the addition rule of probability. And I'm going to show you this visually because I think it will make more sense visually. There are two events that are possible. So let's consider this one as being the store not having what we want, and this one as being the red light. We want to know what is the probability of A or B. And so what I've done is I've set up this Venn diagram, and you can see that this circle represents A, this circle represents B, and the overlap represents both of them happening. Okay, both A and B happening. We want to know the total area of the circles, all the circles, because that's the probability of A or B happening, is the area of all the circles. So let's start out by just saying event A. So you can see that I've colored this in. Here's the probability of event A. That's the store not having what we want. Now let's add the probability of B. This is getting the red light. And you can see that by adding these two probabilities together, what's happened is we have a double count. Do you see how we've double counted the amount in the middle? And I've turned it purple because it's the combination of red and blue. So the problem is we've overcounted, and that's how we get this 125%, is because we've double counted the overlap. But the good news is we can correct for this. We can correct for this. All we have to do is subtract both of them, and that fixes it. And so that's what you do. You take event A plus event B minus the overlap. And that way the overlap only gets counted once. So once again, because this is confusing, we did event A plus event B, which gives us 2 of the overlaps. And so we just subtract both of them happening, and now it's fixed the problem, and we now have the formula. And so that's where this formula comes from. To find the probability of A or B, it's the probability of A plus the probability of B minus the overlap, so that we only get one overlap. By the way, when I write P of AB, that automatically means and. So the probability of AB means A and B happening. So that's an important rule that you may want to write down. So from our example earlier, we know that the probability that the store doesn't have what we want is 40%, and the probability of a red light is 85%. And we were able to calculate both of those happening by just multiplying them, because they're independent. One does not have an effect on the other. And so we multiply them to get 0.34. And so now that we have all these numbers, we can plug them into the formula. So what's the probability of one or the other happening? It's the 40% plus the 85%, just like we did earlier, but we subtract the overlap. And when we do that, we get a final answer of 91%. So you can see that it's pretty likely that one or the other is going to happen. It's pretty likely that we'll get a red light or that the store won't have our item that we want. And that's because one of those probabilities is 85%, one of them is 40%, and the way we combine those is by using this rule. We add them together, subtract the overlap of both of them happening, and that arrives us at our answer of 91%. I know that's a little confusing. Hopefully I've done a good job explaining it. One thing that's fun about this rule is that you can extend it to 3 events, or 4, or 5, or 6, or any number. The way that works is you add up all of the events, then you need to subtract all the double overlaps, but then you've subtracted too much, and so you need to add back in the triple overlaps, but now you've added too much, and so you have to subtract the quadruple overlaps, and it gets really fun and confusing. So luckily we're only going to need to worry about 2 events, so you don't have to worry about that, but this formula does get kind of fun as you have more and more things to consider. Okay, so I've already mentioned this definition. Compound events are when we have 2 or more events happening, one after the other. So an example is flip the coin 3 times. Those will be compound events because you're doing more than one thing. So I've mentioned this word before, and now we're going to bring it home. Independent events versus dependent events. An independent event is when an event has no impact on the next thing that happens, or when something happens that had no influence from anything that happened before it. And so everything we've looked at so far have been independent events. And the nice thing about independent events is that their probabilities are really easy to calculate. Again, we literally just multiply them together if they're independent. So you can see that these two were independent, and so we multiplied 0.40 times 0.85 to get 0.34. Really easy to calculate independent events that don't have anything to do with each other. It's much more difficult to calculate the probability of dependent events. There is a formula for it, which I will show you in a second, but it's much more challenging to calculate the probability of dependent events. Now, there's a rule in probability and statistics that we're going to follow, and the rule is this. This affects us because we're going to be giving a survey to hundreds of people when we do a statistics test. But the problem is when we do that, those events are dependent, which means they're hard to calculate. And the reason they're dependent is this. If I'm giving a survey to somebody and then I randomly give out another survey, I don't want to give the survey to the same person twice. And so you can see that the probability has shifted. The first survey could have gone to anyone, but the second survey could have gone to everybody minus that person. And the third survey goes to everybody minus those 2 people. And then the next survey goes to everybody minus those 3, and then those 4, and then those 5. And every time we're changing the sample size, and that makes the probability really hard to calculate, because it's a different sample size every time you hand out a new survey. I hope that makes sense. And so, but luckily, the probabilities are really similar if our sample size is less than 5% of the population. And so if you have 10,000 people and you give out 50 surveys, the probabilities for the dependent and the independent are so close that we can just go with the independent and make our lives easier. So that 5% is kind of arbitrary, but the probabilities are really close if we're less than that 5%. So when we're doing a survey or a sample or doing statistics, it's generally not good if our sample is greater than 5% of the entire population. Because if it's greater than 5%, you're going to start to get errors with your math because we do this simplification. So we could go much more into detail on that, but I'm not going to. I believe this is a question on your homework. That's why I included it in the spreadsheet, in the slideshow. So that's why we do it. To make the math easier, we'll keep our sample size less than 5% of the population. So let's actually see the difference between independent events and dependent events. So here we go. Imagine we have a bag of marbles, and there's 3 yellow, 10 red, 15 blue, and 6 green. Okay, these are our marbles, and we don't want to lose our marbles. Just kidding. What's the probability that you pick a yellow marble, and then you put it back in the bag, shuffle the bag, and then pick a red one? So you can see that there's 2 events here. First, we put in a yellow, we shuffled the bag, and then we picked a yellow, put it back, shuffled it, and then picked a red. Because we shuffled the bag both times, those are both independent events. One did not affect the other. And so as a result, we just multiply their probabilities together. So the probability of picking, as usual, again, I should have mentioned, find the total. We need to find the total of 34 marbles. And you got that by just adding all of these together. As I said, since we are replacing and shuffling, the events are independent. So the probability of picking a yellow marble out of the total is 3 out of 34. We put it back, we shuffle, and so now the probability of picking a red one is 10 out of 34. And to find those probabilities, you just multiply them together, and we get 30 out of 1156, and so 2.6% chance. So really unlikely in this bag of marbles, really unlikely to pick a yellow one, put it back, shuffle, and then pick a red one. It would only happen 2.6% of the time, not very likely. Notice how when we do compound events, the probabilities get small quickly, and the reason is because you're taking a fraction of a fraction, and so those numbers get small quickly. Even with 10 out of 34 for one of our events. Okay, now check out the difference between that question and this one. On this question, we have a bag of marbles that has 5 purple, 4 orange, 20 green, and 2 pink. Okay, so we have a new bag. But this time, find the probability of doing a green marble, don't replace it, and then pick an orange marble. Okay, so we have our bag. We're going to pick a green one. We don't put it back. We shuffle the bag, and then we pick an orange one. This is now a dependent event, which means it's a little bit trickier than an independent, because the second event depends on the outcome of the first one, because we're assuming that we picked a green one and then pulled the green one out of the bag. Watch how we fix this. As usual, first we find the total of 31 marbles. That's 5 plus 4 plus 20 plus 2. So far that's the same. Picking a green one is the same. There's 20 green marbles out of 31, so it's 20 divided by 31. That's the same. Okay? But now we need to think a little bit for the next event. We're going to multiply just like before, but what is this probability going to be? What is this probability going to be? Remember, we're going to assume that this happened in order to calculate this probability. Can you think of what we're going to do? I'll give you a hint. It involves the total. Since we are going to assume that we picked a green marble with a 20 out of 31 chance and then did not replace it, now we're going to pick an orange one. There's 4 there, but it's going to be 4 out of 30. Do you see what I did? I dropped the total by 1 because we put the green one out and we didn't replace it. And so now there's 30 marbles instead of 31. And so it's 20 over 31 times 4 out of 30. You can see that this event, influenced this one, and that's why the total changed. Other than that, everything else is the same. 20 times 4 is 80. Multiply the denominators together to get 930. Remember when we multiply fractions, it's top times top, bottom times bottom. Then I divide that, convert it to a decimal, then convert it to a percentage. So in this bag of marbles, there's an 8.6% chance of picking a green one, don't replace it, shuffle, and then pick an orange one. Let's do another example of that. I think it'll make sense after this one. We have a new bag. We have 5 purple marbles, 4 orange, 20 green, and 2 pink. We are not replacing the marbles. What's the probability of picking a green one, then an orange one, and then another green one? Again, we're not replacing the marbles each time. These are dependent events because these 2 events depend on what happened before it. Let's do it. As usual, first we find the total. So there's 31 marbles if you add them all up. The first green marble is fine. There's 20 green marbles out of 31, so that's just 20 out of 31. No big deal. And we remember from the last example that because we've now taken one out of the bag, there's now only 30 marbles in the bag, so we multiply that by 4 divided by 30 because there's 4 orange and now 30 total. Now we're going to pick another green one. So what number goes here if we're picking another green one? Again, we're going to assume that both of these happened, and then we're going to put in the green one. Here's the trick. You probably thought already we're going to drop the denominator by 1, which is true. The denominator is going to be 29. But what else has happened? Notice that we've already picked a green marble out, and we didn't replace it. So that means there's one less green marble there as well. Do you see that? So there's one less green marble, and so that means it's going to be 19 out of 29. So the denominator dropped from 31 to 30 to 29 because we took out a marble each time. And this number was 19 because we started with 20, but then we assumed that we picked one, and so we got 19 remaining. Again, multiply the 3 numerators together to get 1520. Multiply the 3 denominators together to get this big number, 26,970. Divide, convert to a percentage, 5.64%. Hopefully that makes sense. If not, please email me a question. I'd be happy to answer it. Or if you'd like to see another example. Here are some final examples, and then I think I'll stop this video. We have George Washington versus Abraham Lincoln, who are running for president. And you can see how many social media posts they made. TikTok, Instagram, Twitter, and Facebook. As usual, I hope it goes without saying that the first thing we should do is find all the totals of everything. And so that's what I've done. We found all the totals for Lincoln and Washington. We also found the totals for Facebook, Twitter, TikTok, and Instagram for the total of 8,332 posts. Let's answer some questions about this. Assume that the selections are made with replacement. Okay? What's the probability of picking a post that is from Instagram and then a second post that's from Instagram? Well, you can see here that we have 335 posts from Instagram out of the total 8,332. Notice it says with replacement, so that means if we pick a post, we're going to put it right back in and then pick again. And so because of that, the numbers don't change. These are independent events because we put the post back and then randomly select it again. So Instagram, then Instagram, all the numbers stay the same. It's 335 over 8,332 times 335 over 8,332 for a probability of 0.001616. So really unlikely. Really unlikely. Less than a 1% chance. 0.16%. Now, this might seem like a silly example, but I can tell you a lot of probability analysis is built both into the rules of social media companies and how they do their algorithms, as well as people trying to game those algorithms so that their posts get more reach. And so we're just touching the surface of the analysis that we do on internet, social media companies, and internet traffic in general. Here's another example. What is the probability of picking 2 posts from TikTok? This time, assume that the selections are made without replacement. Okay? Well, in that case, now we have dependent events. So we had 103 TikTok posts out of 8,332. We're going to pick one, and then we're going to pick another one, but we can't pick the one we already picked. And so as a result, notice what happens. The TikTok number goes from 103 to 102. Because we've picked a TikTok post that we can't pick anymore. And the total has gone from 8,332 to 8,331, again, because we've picked a post that we can no longer pick again. So that's how you do that, and the probability of this is really small. Multiply them together, 0.015%. That's really, really unlikely. About 1.5 out of 10,000 chance. So very, very unlikely. I hope you understand why this went from 103 to 102 and 8,332 to 8,331. It's because we did not have replacement, so they were dependent. In the next example, what's the probability of picking a post that is not from Twitter? Okay, what's the probability of picking a post if we picked randomly that's not from Twitter? There's two ways you could do this. You could add up all of the totals of things that are not from Twitter and then divide that by 8332. Or you notice that this is the complement. So if it's the complement, what we could also do is 8332 minus Twitter, and that'll tell us the number of posts that are not from Twitter. So feel free to do it either way. I did the complement method. So I said, what's the probability of not Twitter? That's 1 minus the probability of Twitter, because it's the complement. And so that's 1 minus 7269 over 8332. So do that decimal first. So 1 minus that decimal gives us 0.12758. So non-Twitter posts are 12.76% of the population. Example 4, what is the probability of picking a post that is not from Lincoln? Now we're going to use these totals over here. So the way you do it is you can either just take Washington and divide it by the total, since we're doing not Lincoln. Or again, you could do the complement, do the total minus Lincoln, which would give you Washington, and then do that number divided by the total. So notice that either method that I just described gives you the answer. So you can either do Washington divided by the total, which gives you 38.86%, or you can do the complement, which is 1 minus Lincoln, which again gives you the same decimal and the same percentage. So whichever way you would like to do. It's very common with these probability questions that there's more than one way to get the answer. On a sensitive part that goes on a submarine, 305 out of 4,000 were defective. The government will test 3 of them, and if they all pass, the batch is accepted. What is the probability of accepting the batch, and is this procedure a good idea? Okay. 305 out of 4,000 were defective. We're going to test all 3 of them, and if they all pass, we accept the entire batch. So we need to calculate the probability of accepting the batch. Here's how we do it. If all 3 of them, as I just said, are not defective, then we accept the batch. But note that these are dependent events. And so we want to know what is the probability of picking one good one, then a second good one, then a third good one. So that's what the probability we're going to do. And so notice that I'm going to do the complement, 4,000 minus 305. So you can see that there's 3,695 good parts. So 305 are defective, 3,695 are good. We need that number to calculate the probability. Watch how it works. The probability that the first one is good is, as I just said, 3,695 out of 4,000. But now because these are dependent events, we now can't pick that part anymore, and so there's one less good part and one less in the total. So the probability of testing the second one being good is 3,694 out of 3,999. And then finally, the probability of picking a third part that's good, again, we need to take one good part away, and we need to take one out of the total. And so the third one is 3,693 out of 3,998. Hopefully you can see that this is real similar to the marbles in the bag. Please let me know if you have a question on this. I know it's a little confusing. Multiply all of these fractions together, and you get that the probability of picking 3 good parts randomly is 78.82%. So is this a good method for testing the parts? Well, we can see that 305 of them are bad. Like a little bit less than 10% of the parts are bad, but we have a 78% chance of saying that the batch is good. So to me, that's terrible. Would you get on this submarine? I sure wouldn't. So we need we probably need to test more parts, because a lot of batches are being accepted, even though a good chunk of them are bad. And so you can see that testing 3 of them and seeing that they're all good is not a good procedure, because we're accepting this terrible batch 78% of the time. Real life stuff is done with this, like in engineering and figuring out the rates of error that parts can have. So we're only doing the fundamentals of this, but believe me, these kinds of calculations are done in engineering and in other fields in science to test things. So as I said, this is not a good procedure because there are so many defective parts. Again, would you get on the submarine? I sure would not. Here's one last one from your homework. The probability of event X is 0.023. What's the probability of the complement? Well, hopefully by now you know this. To find the even though we don't know what the event is, the probability of the complement is just 1 minus. So we do 1 minus the probability to get the complement. So 0.977 or 97.7%. Remember that little c means complements, the probability of X not happening. So the probability of X happening is 0.023. The probability of X not happening is 0.977. Happening, not happening. Notice it adds up to 100%. And I'm going to stop this video right here. And so in the next video, we will cover section 4.3. Thank you for sticking out this long. I really appreciate it.